I guess today we have to discuss some open problems, but most of the open problems are going to be motivated by some motivational examples of graphs that are indistinguishable by the methods that we've by the algorithms that we've discussed. So let's just start by talking about a few of them. And luckily for me, Akihiro has already defined one of them for me, the Hadamard graphs. So as he mentioned this morning, these will be diameter 4, distance regular graphs, which are both antipodal and bipartite, and they are also triply regular. But let's see a slightly different definition. He has very nicely written for us exactly what the adjacency matrix and the distance matrices look like. So let's give the combinatorial description of what this is. So these graphs are distance regular, antipodal covers of the complete bipartite graph K and N, or as Chris Godsell or as Chris's camp calls them, they're drachens. Drachens. With an extra sound.
Chris has ever called his graphs that?
Draken.
I don't recall seeing Krystal doing that.
Oh no, he has definitely done this. He makes a difference between Draken, like with one N, and Draken with two N's.
Okay.
He's not here to object, so you know.
Yeah. That might just be the reason.
Anybody doing Drakens, there's definitely papers where they're called that. So how do you construct them? Well, they're double covers of K and N. So the double cover of K and N, how do you get it? Well, you take the vertices of K and N and you replace them with two vertices. So we obtain them by replacing each vertex of K and N with two vertices, okay? And then we take, we have our Hadamard matrix, and now, so for each two vertices, so for each pair of vertices in the left side of the K and N and each vertex on the right side of the K and N, you have four vertices. Yeah, row vertices and column vertices, and then you join them with an equal sign when the entry in the Hadamard matrix is a 1, and you join them with an X when the entry is not 1. Okay, so the Hadamard matrix is H, and then we join, okay. So for an adjacent pair of vertices, we join the four new vertices, or the two pairs of new vertices with an equal sign. If H, so two parallel edges, I mean, these vertices, there's a vertex 1 and vertex 2 attached to each pair. So we join 1 to 1 and 2 to 2 if the appropriate entry, the corresponding entry H is 1 and with an X. So yeah, this is going to be a double cover of K and N, and it will work out that it turns out to be distance regular, and Akihiro already gave you their parameters this morning and all the relevant information, so I don't have to. But I do maybe have to tell you about how they're indistinguishable. Oh, yeah. So maybe before that, let us return to this part here that I've written nothing in. So I think today the focus will be, we will see several families or several graphs which are not distinguishable via routine of M's and all, or not distinguishable via k-dimensional Weisfehler-Lehmann. And we can take this to those that are not distinguished by M's, we can take those as candidates to be two equivalent. We consider them to be candidates for two equivalent. So this Hadamard thing, Chris and I have some very long-term ongoing work where we are trying to show the entire family is not distinguishable, any two of the same order. But before I do that, I have to tell you how to make different graphs using different Hadamard matrices. So two Hadamard matrices, H1 and H and H prime are equivalent, Hadamard equivalent. Lots of notions of equivalence here. They're Hadamard equivalent. They're Hadamard equivalent if one of the following holds. If H is obtained from H prime, a series of the following operations. So first, you can permute rows. So yeah, by series of the following operations, permuting rows, permuting columns are surely legitimate, and multiplying rows and columns by -1, and multiplying columns by -1. And one more thing, there's one more way in which two Hadamard matrices ought to be considered equivalent. Yes, Bill, the transpose and taking transposes. So Brendan McKay's paper where he proves the next lemma, he actually missed this thing, but it's okay. Okay, so there is a theorem of Brendan, a very early paper, probably when he and Chris were office mates and they were PhD students, that the Hadamard graphs corresponding to H and H prime are isomorphic if and only if H and H prime are Hadamard equivalent. So it is an ongoing work that we have slightly paused because we wanted to do this matrix algebra approach instead, and also it was very time consuming. But Chris and I had an ongoing work where we wanted to show that Hadamard graphs are not distinguishable. Hadamard graphs of order n are not distinguishable by the EMS algorithm. But definitely computationally, you can compute some of them. There are many that are smaller than 100 vertices, and those are all not distinguishable. So for n equals 16, 20, and 24, these are the smallest orders on which there are multiple non-Hadamard equivalent Hadamard matrices. There are multiple Hadamard graphs of order n, which are not distinguished by the spectrum of the EMS matrix. And I did check this, that the Hadamard graph of order 4, it has 16 vertices and happens to be isomorphic to the 4 cube. I computed the basis for its second extension, so W2, and it has 26 generators. So I don't know what to make of it, except that I think this is the correct number if it were to just be the Twillig algebra. Okay, so for example, the Hadamard graph happens to be isomorphic to the 4 cube, has 26 generators, or 26 elements in the 0, 1 basis of its second extension, W. So I don't know if you want to do some numerology. Here you go. I was not able to compute the next order because it's large. This is some family. So another family comes from Jamie Smith's PhD thesis. I don't want to call them Smith graphs because there are other Smith graphs that are about to come up. Jamie graphs. So what are we? 4 eigenvalue examples. 4 eigenvalue examples. This I'm not actually going to define. So, but basically what happens is Smith has a family, an infinite family, whose number of vertices will be powers of 2, or some very small variant of that. I think they can only be powers of 2, and they have 4 eigenvalues. And so there's an infinite family of these graphs, and then he can get together with cospectral mates with respect to the adjacency matrix, obtained via generalized Gatso-McKay switching. And these are not. These he can prove are 2 equivalent. And it comes from some sort of geometric construction, but they are not strongly regular because there are 4 eigenvalues and not 3. And then of the other graphs, there are many sporadic examples, small sporadic examples. So there are some small examples. So for example, in the original paper, so Ems et al., in their original paper, they did have some regular graphs. They did compute some regular graphs that don't have, that are not distinguishable. There's one pair of 4 regular graphs on 14 vertices from the original paper. Gordon Royal computed for us a pair of cubic graphs on 16 vertices. Okay, and I will say a bit about these after I type them all. And then another pair that I found when I was doing my master's thesis, wherein you can construct a Desargues graph. It is a distance regular graph. Also, it is the double cover of the Peterson graph. Peterson graph has an independent set of size 4, which Bill calls the hands and the knees of the Peterson graph. And if you switch on the images of these 4 vertices on the left side of the Desargues graph, you can create a cospectral mate of the Desargues graph. It has a unique cospectral mate. So only one other graph that's cospectral to the Desargues graph, which is not distance regular. And it and its cospectral mate are also not distinguished by this procedure. Okay, and these 3 pairs, 3 sporadic pairs, are all related to each other by Godsell-McKay switching. Do I need to define Godsell-McKay switching? Okay, so Godsell-McKay switching, there are various yeah, I didn't want to define it. Okay, but anyway, let's just do it. Where is the thing? Okay, this was for Hadamard matrices, but I actually did not draw the diagram. So a Godsell-McKay switching set is, suppose you have your graph, which is, you know, this nebulous cloud, and then there's a subset of vertices somewhere that induces a regular graph. So whatever this set of vertices has to be, this in here, it has to induce R regular, and it's only in a regular graph. So in a regular graph, you have some subset of vertices S, which induces a regular graph S. So you have S versus the other part of the graph, which will be like a square box, maybe. Okay, so for the other vertices in the graph, of which I will draw 1. This other vertex has 3 options with respect to this. Either this other vertex is adjacent to none of the vertices of S, well, that would be the easy vertex, or this vertex is adjacent to all of the vertices of S, or this vertex is adjacent to half of the vertices of S. How do we depict this? Okay, let's cut it in half, and then we connect it to the thing. Yeah, okay.
That's a very good job. Oops.
Go to the side. Go. Okay. Beautiful. Yeah. Okay. So anyway, this vertex is adjacent to half of them. So you need a subset of vertices S such that in the rest of the graph, every vertex has this property. So once you do this, you can take those vertices who are adjacent to half the number of vertices. This blue situation here, it's about to be blue. Don't worry. Okay. Okay. Actually, a lot of things became blue. Okay, so this blue situation here, for all of these, instead of it being adjacent to this half, you can delete all these edges and add all the other edges. So it will still be adjacent to half these vertices afterwards, but the other half. So this is some operation that does not change the degree of any vertex in the graph. Because for those which you deleted neighbors, you added back neighbors, and it will be also correct for these vertices up here. And this will create a cospectral graph to the original graph. And it's not always isomorphic. The Peterson graph itself, of course, it has an independent set of those 4 vertices, the hands and the knees. And if you did this, it would be a Godsell-McKay switching set. But it has no vertices that are actually, it does have vertices that are adjacent to half. But after you do this switching process, the new graph you get is also the Peterson graph. So it's truly very lonely, no cospectral mate. But sometimes when you do
Changes the degrees of the verses in S.
no, you're right.
Doesn't change the sum.
It doesn't, yeah.
Yeah.
Yeah, it doesn't change the sum. Okay. So anyway, this bottom part will be arranged.
The bottom part is fine.
But the original graph is regular. Original graph is regular, and this induced graph is also regular. So if there was a vertex adjacent to this half, then and nothing adjacent to some vertex in here, then it would this whole thing would not be regular. So it's a local thing. That in the end, this will be regular. It's a non-trivial argument. For these vertices here, it's absolutely trivial that their degree sequence is unchanged. But these up here, you need the original graph to be regular, and you need this induced thing to also be regular. Yeah, and I think this fall also has to be regular. And there's more generalized switching where you partition into more parts, and you can do different things for the different parts. But it will still result in a co-spectral graph that is not always isomorphic. All these three pairs are related to each other via Gauss-Mackay switching, this procedure here. They're also related by like a more brutal form of switching where you can just pick two edges in the graph, delete them, and now there's like two pairs that you could add, and you add one of the pairs back on the same vertex set. So there's always some way to untwist these to get the other one. But we don't really know how to do this. And Gauss-Mackay switching, Chris actually, at first we thought maybe this is something that would cause the M's matrices to be indistinguishable, but it's not, because for example, the chain graphs, they're all related to each other via Gauss-Mackay switching, but they are all distinguished by the spectra of the M's matrix. So it's not sufficient on its own. Okay, and then also sporadically, there are some other examples. You can find Drac-Ns with one N. So there are, how many other? There are 15 strongly regular graphs, conference graphs on 15 vertices, 25 vertices. There are 15 strongly regular conference graphs on 25 vertices. So we can use them to sign the edges of K25. For each signing, non-isomorphic two covers, which are going to be Drac-Ns, distance regular, which in this case, which is 25. So Drac-25s. And these are, some of them are not distinguished by this. Yeah, so under the whole matrix, there are 4 cospectral classes of sizes 1, 2, 4, and 8. So if you want to investigate why it is that some of these are cospectral to some other ones, there is some, and I don't know why they're powers of 2. It just happens. It does sum up to 15, right? And I think that class was enumerated by exhaustive search. So there are exactly 15 graphs. So on the Bauer website, it should have like an exclamation mark. Some sporadic examples that could give you ideas to how it could be that graphs are not too equivalent. For none of these, yeah, I didn't compute the extensions for any of these. So I don't know if they are equivalent. But like these down here, they seem kind of small. So maybe that could be possible. The next graphs are the CFI graphs. So Kai Führer. Emily can pronounce it for us. Just let me find.
Presuming it's like matching it up, because I've been so confused by this. Is it Jaeger?
Jaeger is a French
Like
person.
German, this French pronunciation of German names is like throwing my brain.
Jaeger is a French person. He's François Jaeger, so his last name will be pronounced in French.
But it is definitely a German name.
Yes. Yeah, it means hunter. We know.
I'm not saying.
So a separator. So a separator in a graph. So to do this, okay, so what do they construct? They construct graphs that are actually K equivalent for arbitrary K. But the things, they are going to be regular. So in the end, this will result in cubic graphs that have maybe many eigenvalues, but they will be K equivalent for some appropriate K. But to tell you the K, I have to define what a separator in a graph is. So in this like computer sciencey sort of setting, a separator in a graph is a subset of vertices, such that its deletion, the induced graph of V minus S, has no connected component with at least half the number of vertices. Yeah, the induced subgraph on V minus S has no connected component, at least V over 2. So what did so these CFI graphs, so Kai Führer and Immerman, now that I'm just gonna, so in this paper, let's replace them. show that that they have a construction. It takes as input some cubic graph who has a separator of size k. Have a construction which takes in a cubic graph with a separator. A cubic graph where the smallest separator, so with no separator of size k minus 1. Okay, and outputs two graphs, let's say G sub k and H sub k. Puts G sub k and H sub k, which are cubic and not distinguished by the k-dimensional Weisfehler-Lehmann. And in fact, they're k equivalent, I think. Oh, sorry, they're not k equivalent. They're going to be k over 3 equivalent by the previous result. So what is it that they do to these graphs? Okay, well, pictorially, we will only look at it for K4. Okay, something happened, so it made this page. Okay, so what does it do? They define this little auxiliary graph, which is x3 because the vertex is degree 3. And here you have two pairs of vertices for each outgoing edge of this original vertex. So you're going to put this widget on every single vertex. And then for each vertex, you know, you're going to name the edges somehow, like the first edge, second edge, third edge. Sorry, the first, second, and third edge coming out of my vertex. And for the next one, I also have the first, second, and third. And then I join the pairs. So for example, for this vertex in the middle, I'm considering this edge going above to be the first edge leaving this vertex here. So I'm connecting the A1s and B1s with A3 and B3 from this vertex here. Okay, it's happening. And I get a huge graph. It's cubic, as you can see. So this is a thing that you get from K4, which is a cubic graph whose separator, it has no separator of size 2, because if I delete two vertices of this, I have a component of size 2. Okay, so this will result in something that is right, so it's not distinguishable by two-dimensional Weisfehler-Lehmann. Smallest separator has size m plus 1. There's a +1 that could be off. I'll fix it when I upload the notes. Okay, but this, how do you get the other graph? So in the other graph, you just cross one of these things. So you delete these and then you put them in the other way. So here, for example, you have like A3 being connected to A1 and B3 connected to B1. You would just delete them and connect A3 to B1 and B3 to A1. So this creates a twist, and there are some rules about how many edges you have to twist and where the twist can be depending on the complexity of the graph. I've chosen the easiest graph, like the smallest cubic graph. So there was actually no choice. I can cross any edge, and I would obtain another graph that is not isomorphic, but will be indistinguishable by the k-dimensional Weisfehler-Lehmann. Okay, so this particular example is not known to be two equivalent because I need to divide by 3 to use the original lemma. However, it is still cospectral also with that M's matrix, this pair that I will get in this way. I can cubic graphs with larger separator numbers exist, so there will be graphs that are not distinguishable by the 6-dimensional Weisfehler-Lehmann, and they will be known to be two equivalent. And the other thing that maybe you can notice is that this will not be distance regular. This particular one is not, and even if you have the larger ones, because I think if you look at the eigenvalues of x3, yeah, it would be very hard to construct something that is distance regular out of this, and definitely not strongly regular because the diameter is way too big already. Okay, so that's the third infinite family. So every family has sort of its every example that we are able to find has upsides and downsides. So this family, people were able to show that it is k equivalent for some k and for some input of the separator size, but it's not strongly regular. In fact, that has been the problem with all of the previous ones, that they are not strongly regular. Okay, so finally, I'm going to show you how we constructed those strongly regular counterexamples. And maybe I don't have to be very, very rigorous so that we could go for beers after this. But also, there is not enough time to detail the construction of how this occurred. So the generalized quadrangle, GQ, the point graph of GQ QQ squared. So this is going to be triply regular because it is a Smith graph, by which I mean that one of the crime parameters vanishes. So this has to be triply regular when it exists. And there is at a point for Q at least 5, or rather, there's a possibility of having a non-isomorphic pair of them. And the first time that such a thing occurs is for Q equals 5. For large Q, there are multiple constructions for these generalized quadrangles for GQ squared. Well, therefore GQ squared Q, but we just take the dual. And the first time, which could give non-isomorphic graphs, the smallest of which occurs. So these are the graphs. These are the strongly regular counterexamples, M's procedure. Are strongly regular. Maybe I will just draw a picture of how they are constructed. Least bad board. It slid down. Okay.
No, you can.
Where is the? Okay. I got it. Okay, fine. Okay, I'll hold it. Okay, so I'll just draw the picture for you in 3D in R to the 3. And then you just believe me that some similar structures can occur for in finite field. Okay. All right. Okay, it's fine. It's working. So you have a cone, right? So this is like the infinite ice cream cone and the 2 copies of the infinite ice cream cone. If you intersect the cone with a plane, which is a hyperplane, you intersect it, you get some things like you had in like high school, yeah? So you can have an ellipse, you can have a parabola if you intersect it like this. If you intersect like this, you can have your hyperbola, right? It's like a curve. Okay, all right. But if you did this not in R to the 3, but in the projective plane, the projective geometry of dimension 3, then you can still define what it means to be a cone. And all the possible ways of intersecting your cone with a hyperplane, except when it intersects only in that point, they give you something called an ovoid. Okay? And now if I take my cone and a point that is not on the cone, and I take all possible hyperplanes through this point, which intersect the cone, not at this point, at the other points, it partitions the points of this cone into ovoids, into many ovoids. And what I have just shown you, this partition is called a flock, because like a sheep is like an ovoid, and like a group of sheep is a flock, right? Like ovine, right? Okay, and what I've just shown you is what's called a linear flock. It's a linear flock if it's constructed by taking a point, all possible hyperplanes through the point, and the partition into ovoids given by all these intersections. But this is just a cone. It's just a set of points in the projective space of dimension 3. And there could be some other partition of these things into ovoids.
So does it need to be like this kind of thing, or do you just mean any like convex cone you start like intersecting with hyperplanes? Or
no, it has to be this cone. It is this cone, but it's in the projected geometry. It's in a finite over a finite field in a finite geometry, so it behaves sort of strangely. And anyway, there are other ways of partitioning it into ovoids, and if it does not come from this business, it's a nonlinear flock. Okay, and the point is, from every flock, linear or nonlinear, you can construct a generalized quadrangle of q squared q order. Q is this was over GF of q. Base field of this was GF of q. This is this q. And if the flocks are not the same, for example, one is linear, one is nonlinear, this would result in non-isomorphic GQs. So this is the first order on which there are non-isomorphic GQs that we could use, and they are not distinguished. And that's the thing. And maybe the next thing is to try to show that these things are also these two constructions of GQs are also, and probably you should just show that all possible flock GQs will be equivalent to each other.
Stays.
Yeah,
Of course.
of course. We've taught it to stay in this position, but maybe it will just slowly slide down during the remainder. So there are two. I think that there does also, I think this is the smallest pair of non-isomorphic GQs of the same parameters. The only other thing that is possible is to construct a GQ q minus 1, q plus 1 from a hyperoval. So you have like a projected geometry, you have an affine geometry, projected plane and infinity, and a hyperoval, and different hyperovals will give you different ones. But the first order that this exists on is already very huge. You need 2 to the 5, the field to be 2 to the 5. So this was the smallest ones that we could find. Okay, and also those other ones are not going to be triply regular. So maybe there's that. So open problems. After seeing these things, first, it would be interesting if you could show any of the previous families that were not known to be 2 equivalent are 2 equivalent, or even any of the pairs. That would be interesting. But most importantly, x and y are triply regular. Are they k equivalent or some k greater than 1? And if so, what is the k? So for this procedure of m's and all, I need k to be 2 to have an infinite family. But does it have to be? But what is the actual truth? Maybe there are 3 equivalent, triply regular. I don't know. If you want the thing that corresponds to triple products, that should be 3. And then also, how does the Juillet algebra Jn compare with w to the k? Could it be that J3 there's some image of J3 is contained in W to the 2? And also establishing, I think the 2 equivalence is a little bit easier if you allow your construction to help you. For example, these graphs here, they were constructed to prove the statement about the k-dimensionalized Fairleben using some languages. And so they're somehow well suited to some techniques. But what are some strongly regular graphs whose construction is suitable for similar techniques? I don't know. So those are some open problems. And thank you to the organizers and to everyone. It's been a very nice week. And thank you for staying all the way to the end of my mini course and not falling asleep, at least not in front of me, not yet. And yeah, so thank you very much. Okay, sorry, okay. Yeah. What?
Okay. Krystal, thank you very much for your mini course. It was
Thanks.
appreciated the new method of delivering talks, and thank you.